Welcome everybody back to another year of Power Hours. Welcome to 2024. We've got a new backdrop here. Some of the same familiar faces, but we're going to kind of go through this systematically throughout the year and follow along with some other programs we're doing through standard. And so this month's topic is fuel injection. Now we've talked about fuel injection over the past couple months here. Darren just did a great GDI session, so if you missed it, make sure to go look in our archive section or find us on our Standard Brand YouTube channel. You can watch that. It's a great session there. Today I'm going to talk about fuel injection, but in a little different manner. I'm going to focus on diagnosing fuel issues or input issues or air-fuel ratio issues, specifically using fuel trims. Now fuel trims has been around for a long time. Back when I started working on cars in the GM world, we called it block learn integrator, and there's some different terms, but it's the adaptation that the engine control module or the powertrain control module makes based on corrections to the air-fuel mixture. So let's take a look at how things have adapted through the years and how we can use it to our diagnostic advantage. All right, so let's jump into the presentation here and just do a quick review of fuel systems throughout the years. So first we had carburation. Now this is a very minimally controlled fuel system. It was kind of preset. It was based on some different jetting and internals of the carburetor and the amount of vacuum being drawn in the system in order to deliver what was an estimated amount of fuel. And so we had a mechanical fuel pump drawing fuel from the tank and then sending in a low pressure, typically about 2 psi, to the actual carburetor itself to dump it into the engine. Very minimal control. Well, then about the 1980s, mid-80s, we started to see throttle body fuel injection. And so then we've got an in-tank fuel pump pressurizing it from the tank all the way up to the engine. On top of the intake manifold, we've got our throttle body there with multiple injectors inside of it, being computer controlled and delivering what we're going to call a quote-unquote precise amount of fuel at that time into the engine. Now this is when we started getting stuff like fuel trims and the adaptation, et cetera, and the vehicle's ability to fine-tune on its own the amount of fuel to maintain the proper air-fuel ratio as desired, not only for performance requirements, but also for emission requirements. Well, by the late 80s, we started seeing port-style fuel injection, in which we had a little higher fuel pressure. Some of these might go up to 45, 50 psi. We're getting much more pressure, and that's gonna change the boiling point of the fuel. It's gonna be a much more deliverable and reliable fuel source going to these port-style injectors. Now these injectors are going to be delivering the fuel directly into the intake manifold itself. And so when the intake valve opens up, it's going to draw in air, it's going to draw in this fuel, it's going to blend it to create the mixture, which will later be combusted inside the combustion chamber. So we've got much better control at this point, but still not perfect. And you know what, we're probably still not perfect, but welcome to today's gasoline direct injection systems, where we're seeing these things idle at about 900 psi, and under RPM, we're seeing up to 2200 psi. And these are much more precise, accurate fuel delivery systems, which are directly injecting the fuel into the combustion chamber itself. So we're not waiting for it to mix in the intake or possibly puddle on the intake valve. It's going directly into the system. So much more precise and accurate fuel delivery. But in many cases, there still needs to be some sort of a correction being made to fine-tune the vehicle. So let's talk a little bit about fuel trims themselves. So we've got open loop fuel trim as well as closed loop fuel trim. And so if we look at open loop fuel calculation here, well, first thing, the vehicle is going to measure the incoming air. Now, if it's got a mass airflow sensor, it's going to take a sampling of the amount of air coming into the engine, and then it's going to look at what's our desired air-fuel ratio. Are we cold? Are we under acceleration? Are we idling? What type of air-fuel ratio is the vehicle looking for based on the engineer's initial calculations? Now, the control module is going to do the math here and say, okay, based on this amount of air and this type of fuel ratio, I'm gonna have to add X amount of fuel to the system to get the desired result, and then it's going to deliver the fuel via the fuel injectors. So relatively straightforward in this open loop, pre-calculated mode. But now once the vehicle warms up, in today's vehicles, we see these things enter into closed loop within 5-10 seconds based on heated catalysts and heated sensors. But again, it's gonna measure the incoming air. It's also gonna look at the desired air-fuel ratio. It's gonna do the math. It's gonna adjust for errors based on inputs of sensors in the exhaust. Now, whether it be air-fuel sensors on modern vehicles or the traditional oxygen sensor, it's going to get a feedback to the PCM and say, whoa, we did the math wrong here. Or we've got more air than we thought or less air than we thought. It's gonna make the adjustment here, being the fuel trims themselves, and now deliver the adjusted amount of fuel into the combustion chamber. So with fuel trims, there's also many different types of terms being used here. The most basic ones are short-term fuel trim and long-term fuel trim. Now think of short-term as immediate correction. When that sensor sees a rich mixture or a lean mixture, it's gonna report back instantaneously, and we're gonna see a quick adjustment on the short-term fuel trim. And so think of this as, if you've got any young kids at home, they're the ones that come up to you, they're excited and saying, Mom, Dad, hey, listen here. And they're gonna tattletale on what's happening. Now, long-term is gonna be kind of the wiser, older uncle. Think of the grand Pumbaa sitting up on the mountaintop there, and it's gonna observe the big picture here. Saying, okay, we've got a lot of reports here from short-term. We need to make a little bit more of a permanent and bigger adjustment here. And so this is gonna be our long-term fuel trim. And so based on the inputs of the short term and observing trends during different driving conditions, the long-term fuel trim will be adjusted. Now, different manufacturers at different times are gonna use different terms on these things. And so if we look at just generic OBD information as mandated by the Society of Automotive Engineers, we're gonna have short term, let's say bank 1 or bank 2, short term bank 1 or 2 secondary, and then we're gonna have long-term and long-term secondary. Now, many technicians are familiar with using OE scan data, and so quite often we're gonna see short-term, long-term. But over the past 15, 20 years now, we've seen new terms introduced here. Lambda, alpha, and so those are using kind of a Greek symbol there, and it's going to use it off a ratio of 1. So the desired stoichiometric ratio of 14.7 to 1 in many cases is gonna be 1. And then we're gonna see adaptations off of that. I'll explain more here in just a second. But if you're working on many European vehicles, you may have run across these terms also, additive and multiplicative. And if you've never run across them, we'll share a little bit of information about those as well, so you're not so surprised the first time you see one. So in the generic world, we've got short-term fuel trim, our immediate correction, and we've got long-term fuel trim, which is gonna be our much slower learned value. And we add them together to get the total trim. So let's say I've got negative 3% on my short-term, and I've got a positive 10% on my long-term. I'm looking at a total trim of approximately 7%. Now, I just did that math here in my head. You can double check on the calculator and make sure I did that right. But we're looking at, over time, we had learned that we need more fuel. But whatever conditions we're in at the moment, we don't need that much fuel. So short term saying, take it away. And so then our total trim being approximately the 7% range there. Now, I know one of the questions that came in already, we'll quickly address that, is what's a good value of fuel trims? It's always been kind of a good value to say plus or minus 10%. No vehicle is gonna be perfect, and so there's always gonna be some type of correction going on there. So based on the manufacturer, you might observe different trends. I've seen some GMs that like to live in that 8% range, or so over time you're gonna learn your own values here. But as long as it's within a plus or minus 10% window and not setting any trouble codes, that's the most important piece here. No trouble codes are set, you should be in good shape. So let's take a look at Lambda. So as I mentioned, stoic, the desired air-fuel ratio will be right here in the middle, Lambda of 1, which is a 0% fuel trim. So that's what we're really looking for, is a reading of 1. Now anything above that value indicates a lean condition. And so as we would expect, 1.05, 1.1, 1.15, etc. If it's adding to that number, it means it's adding fuel. Pretty straightforward, but I'll agree, it's really easy if you're not seeing this every day to overcomplicate this and think backwards of it. So conversely, we've got our value of 1, but if the number is less than that, that means that the air-fuel ratio is rich. There's more fuel than desired there. So the control module is reducing the amount of fuel being injected into the engine here. So if it's on the positive side, the engine's lean and adding fuel. If it's over here on the negative side, the engine's rich and it's subtracting fuel. Now, if you're working in the VW Audi world here, as mentioned, there's these adaptation values here. And so we need to understand that there's going to be different values at idle and partial throttle. If you're familiar with fuel mapping channels and how that all works, you understand that there's different maps at idle versus under load. And so that's what we're seeing here. This is very beneficial, again, for the technician to understand where is my lean condition? Where am I not getting enough fuel, or where am I getting too much fuel? And so we can see a couple different terms being used here in this particular vehicle. Now here's a screen grab from a Nissan application. I grabbed this from a Nissan Rogue out in the parking lot here. And so we can see air fuel sensor. Now we're looking for a 1.5 volt value. That's kind of our median value there. But again, we're seeing alpha 104 and alpha in bank 2 of 105. So that tells me that this vehicle is running a little lean. I'm not concerned about this value at the moment. There's no check engine light on this car. Notice we grabbed this capture at about 1800 RPM. And so this is adjusting and adding just a little bit of fuel here. Now in the General Motors world, this is what a lot of people might be very familiar with. We've got our short-term bank 1, bank 2, long-term bank 1, and long-term bank 2. So if I'm going for my addition, again, we're going to look at short-term bank 1, long-term bank 1, and then focus on bank to bank by themselves here. Now, looking at a different vehicle in the parking lot, just using generic. It's actually a Saturn that we've got in the shop here at the moment. And so just using generic scan data here, you can see 1500 RPM. We're actually running pretty decent on the short terms, but you see on the long term, it's taking away a little bit of fuel here. So nothing to be concerned of, but we wanted you to understand how different manufacturers show different things here. Now, very importantly is we're going to look at the fuel trims under different operating conditions here. Now, as a technician of many years, I still like to observe fuel trim primarily at idle, and then bring the engine RPM up to approximately 3,000 RPM and observe how did it change. And keep in mind, I'm going to be graphing my scan data the entire time. Now I'm going to take the vehicle for a test drive and observe it under light cruise or light throttle as I'm going down the road, and then steady state cruise. In my area, I can go 55 mile an hour without a whole lot of traffic congestion. And so what is my trim doing there? Now, based on what's happening at idle or free revving the engine or during partial load, I'm going to look at how the fuel trims react. And through history and through a lot of studying and knowledge, very much understood what these patterns mean. And so let's take a look at how those transition a little bit here. And I'm going to share with you a little bit of the deductive reasoning I've come up with as a technician and share it with you. Hopefully you can understand as well. So again, as we look at fuel trim kind of mapped out here, think of it as an Excel spreadsheet. So we've got our zero line here in the middle, and then we've got our plus 10%, minus 10%. And as mentioned, we want to look at this during idle, during 3,000 RPM, just revving it up in the bay or in the parking lot. long-term cruise, and then steady state, or excuse me, light cruise. I've been thinking too much long-term and short-term here. Light cruise, and then steady state cruise. Now here's what we see, an example of a typical General Motors vehicle with a contaminated mass airflow sensor. You've all seen it, right? You pull the mass airflow sensor out, it's got like a big wool sweater on it, and there's some contamination on it. Quite often, these things are gonna be not real affected, but they will be adding some fuel here at idle. So while the vehicle's idling in the bay, let's say a 3.6 liter, I'm gonna expect to see about 3.6 grams per second of air being read by the mass airflow sensor. Now, if there's insulation or debris on it, it's gonna act as an insulator, and so it's not gonna report quite as much air at that point. And so we're gonna have this sort of correction, especially as we start flowing more air into that engine. It's gonna exacerbate that isolation, and it's gonna have this sort of effect as we graph out our fuel trims. Now, pirate air is basically a term that's used when air is in the engine that's not supposed to be there, or it's not entering through the correct methods. So think if you've been on a cruise ship, you enter through the correct door to get on the ship. How's a pirate gonna do it? Well, they're gonna do any means possible. And so that's what we refer to as pirate air. This is something, if we've got a vacuum leak or the air boot between the mass airflow sensor and the intake or the throttle body, it has a little crack in it, or the PCV line is left off. Any air that's entering the engine that's not going through the desired amount is gonna be called pirate air. So at idle, we're gonna see a huge correction. But as the engine increases in load and volume of air coming through, that pathway is gonna decrease as a whole percentage. And so we're gonna see our fuel trims come back to normal. So if I hop in a vehicle that's got a check engine light on with a P0171 or a 174 or engine lean code, and then I observe my fuel trims in these manners, that's giving me a really good direction of where I'm going before I even have to pop the hood on the vehicle. Now, if we have an alcohol or low fuel volume problem, now we're talking about alcohol in the fuel, not with the driver, and we need to understand the trends that that's gonna cause here. So if we've got somebody put E85 in a non-E85 equipped vehicle, or if we've got a restricted fuel filter, or we've got a low output on the fuel pump, or even a set of restricted injectors, that engine is gonna be consistently starving for fuel. And so at idle, it's gonna see a correction. It's gonna be trying to add fuel. But as we increase the load on that vehicle and make it work harder and harder, we're gonna see the fuel trims, both short-term and long-term, go up, increase as that engine is starving for fuel, trying to compensate and add more fuel to it. Now this is kind of an interesting one, and this goes very similar with that pirate air conversation. So at idle, we're gonna see an immediate correction, but as we open up the throttle and drive the vehicle, it's gonna come back closer to zero. Now why is that, you're asking? Well, similar to that pirate air conversation, if we have a pin-sized leak cut somewhere in the intake, let's say, we've got a vacuum leak, when is manifold vacuum at its greatest? That's right, with a closed throttle at idle, right? So with a closed throttle, vacuum is gonna be the highest, and so we're gonna be really pulling air through that vacuum leak. Now when we're driving, once the throttle begins to open, as a percentage, that small pin-sized vacuum leak is gonna be much smaller than the throttle body, and so more air is gonna go through the desired passage here, as well as manifold vacuum is gonna decrease, especially as we're under steady state cruise or light acceleration there. We're gonna diminish the impact or the percentage of that vacuum hole compared to the overall throttle opening. And so that's where we see this diminishing change here. And so hopefully you understand why this changes a little bit. So I hope that all those gave you a little bit of insight, and I'm gonna challenge you all to do that this afternoon when you get done with this and go back into the shop or in the next couple days. But let's take a look at some graphing fuel trims here as well. And so that's one of the important things. I've already said it and I want to say it again. It's so important to be graphing our information. It's much easier to see different trends. So if we look on the top line here, we've got engine speed. Then we're looking at short-term fuel trim bank 1, long-term fuel trim bank 1, short-term fuel trim bank 2, and then long-term fuel trim bank 2. So we've got our bank 1 trims and our bank 2 trims here. Then on the bottom we've got loop status. And so keep in mind under immediate acceleration, so if we go back to the top, you see these 4 spikes. This is where somebody's revving up the engine. So under that acceleration mode there, the vehicle enters into open loop power enrichment mode. It's trying to say, you know what? Forget what the O2s are saying right now. We need to go. We got to get out of traffic here, or we got to get across the intersection, something like that. We're going to go back to our pre-calculated fuel delivery pattern here. And so if we look on the bottom, it's open loop. When we're in open loop, we really don't care a whole lot about fuel trims, or they typically go back to 0. And so in open loop, really all bets are off on the fuel trim side. So if we move further down the graph here and we look at the next calculation here where the cursor is, we can see we're a little bit more steady state at this point. We can look at our numbers. We're at 2% on the short term, 1 or 5% on the long term. So we're adding them together to 7, not too concerned. And then on bank 2, we've got a 1 and a 5, really line up very closely with what we're seeing on the other bank, and we're in closed loop. So keep that in mind. Under acceleration, many times you're going to be in open loop power enrichment mode. So when you're observing this, make sure that you're not going into that particular mode. Additionally, on newer vehicles, we're seeing post-catalyst oxygen sensors being used to trim the fuel strategy here. And so there are 2 predominant trouble codes set for those. It's very rare. I mean, quite often, most of the trimming is happening off the front O2s or air fuel sensors here. But I just wanted to acknowledge that there is some correction or fine tuning that's happening by using these rear O2 sensors. All right, so hopefully you got a little bit of background information here, picked up a few tips, but let's put that into practical application. So let's take a look at a case study of a 2011 Chevy Tahoe here. And this isn't a new, really up-to-date vehicle. This is something that's probably showing up in your bays here. So it shouldn't be like a 2024 showing up. But there's some unique trouble codes here, and let's go through the diagnostic process that the technician worked on. Customer's concern is that the check engine light or the malfunction indicator lamp is illuminated and that the engine runs rough. So the technician is going to just pop the hood. This is something we always endorse. Take a look at it. I can't tell you how many times I've popped the hood and there's a performance air intake in there, or even in some cases I've seen it where somebody put one of the turbo encapsulator things in the airflow passage, which is going to set a lot of different fuel delivery issues and airflow issues. So we want to make sure that everything looks as expected, which it does on this particular vehicle. So we're going to scan the engine here, and we see that we've got a P0300 engine misfire detected, and we've also got this relatively unique code here, P219B as in boy, fuel trim cylinder balance bank 2. So in my mind, I'm already thinking here, okay, we've got a misfire and I've got a fuel trim code. I'm kind of thinking we've probably got a fuel delivery problem causing our misfire here. So we want to find out what this system means. So we look up, and actually on the scan tool here, it tells us that the diagnostic system monitors the upstream O2 sensor signals, frequency and amplitude characteristics by calculating an accumulated voltage over a predetermined sample period. So basically it's saying it understands what that sample should look like, and our sample on the vehicle doesn't look like what it was seeing there. And we see that's part of the conditions for setting the DTC. Multiple samples, accumulated voltage are consistently greater than the desired value. So we've got an issue with the upstream O2 signal here. Now that doesn't necessarily mean that we've got a faulty O2, right? It's just doing what it's told. So we don't want to condemn the messenger here just yet. But if we take a look at some of the information that's been stored in freeze frame here, so this happened very recently here. This was in closed loop, engine at 2,000 RPM, 150 degrees, so it was not cold, it was relatively warmed up here. 80% load, so we're accelerating here, even though it's 38% throttle, but still it's under load, we're accelerating. We look at our fuel trims, our short term, bank 1 is 5, bank 2 is 13. So going back with that plus or minus, we're outside that window here. Long term is at 0, probably because we're in somewhat of an open enrichment mode, or we've got a failure mode here. Let's take a look at some more information here. So if we look at the failure record, this was taking a little lighter engine load here, 653 RPM. Short-term fuel trim on bank 1 is 3%. Short-term on bank 2 is 13%. So again, bank 2 is high. This is a little awkward how we get long-term bank 2 here, and then long-term bank 1 is shown there. So if we add them together, bank 1 is about 15%, and we're seeing 18% on bank 2. So it's still significantly higher than what we're seeing on the opposite bank. And then if we look at the fail record for our fuel trim imbalance code here, this is taking about 2,000 RPM, closed loop, set about 23 miles ago. And we look at our trims here. So bank 1 is -2, and the long term on that bank is 5. But our bank 2 numbers, we're at total of about 21. So we've definitely got a leaner condition where fuel is being added on bank 2. Well, what about our misfire? So the technician's going to look at the scan data here. You can see how we've recorded it here. We can see the startup. We got a little bit of an engine flare up to 1,400 RPM, and then we're at 600 RPM right here. The technician looks through all the different cylinders, and we see that number 6 is our predominant misfiring cylinder here. And if we think how these are laid out, cylinder number 6 is going to be laid out on bank number 2. So could this correlate with our fuel trim code that's being set there? Now, it's hard to show all the data here with keeping this a relatively short story. I don't want to show the rest of it, but it was noted that the misfire seemed to be lessened when the technician was driving it down the road. So this is predominantly an idle-related concern. Now, misfires off idle can be a lot of different things here, but again, with experience, in my mind, I'm not thinking I've got an ignition-related problem here yet. Predominantly, we're going to see our ignition-related problems occur under heavy load, where we're loading that ignition coil. So I'm thinking maybe we've got some sort of vacuum leak here or some sort of fuel starvation issue that's occurring with this vehicle at idle. Now, it could be a mechanical issue, could be a leaking valve of some sort. We can go down that path for sure, but knowing that we've got a fuel trim issue as well as an on-idle issue here, I'm kind of thinking a little bit, and this technician was as well, a little bit down the fuel delivery path. Now, I know the questions are going to start coming in here of like, well, if it's an injector issue, wouldn't it get worse under load? Depends. Sometimes the wider the pulse width on these things, we're going to deliver just enough fuel, or if it's a drippy injector, or we're going to scavenge. Remember, this is not a GDI vehicle. This is a port style. And so there might be some scavenging effect throughout the intake there to fuel this cylinder off idle. So as we continue to look at some of the information here, 600 RPM, fuel trim, bank 1 is 2%, and long term is 2%. Bank 2, 1%, but it's growing here and continues to ramp up. So this is the test we're going to do, or that the technician did. I've got the little setup here that I can just show you. We're using a Pico lab scope, and he's got a pressure transducer, and he's actually able to thread this onto the fuel rail. And so he's going to use a scan tool, and many of you have been doing this for a lot of years, where you go in the scan tool, but you were doing it with a mechanical gauge. And by doing a pressure transducer, it allows us to graph it out, and we see probably a little more accurate results. But the test the technician is going to be doing is built into many of the aftermarket scan tools, where you're going to do an injector pressure drop test. And so it's going to power up the fuel pump, it's going to cycle each injector a certain amount of times, and you, the technician, need to observe and record the amount of fuel pressure that's being dropped. Some people might not necessarily like this test because, again, it's a relatively static test. Sitting in the bay, we're not really stressing out, but where was this fault happening? That's right, it was happening at idle. So this technician used this. I've got an example here of a newer Ford fuel rail. This one doesn't have the port to hook up the gauge. It's actually got its own fuel rail pressure sensor. And so in that case, you can actually monitor the scan data while you're doing it here. The vehicle this technician's working on here, this 2011 Tahoe, did not have that opportunity, so he's using the pressure transducer. So let's take a look here at the results. We can see where the PCM powered up the relay and pressurized the fuel system. Now it's going to cycle cylinder number 1 injectors, so we see the pressure drop a specified amount and holds it. Now the PCM is going to power up the fuel pump, build some pressure again, and it's going to command cylinder number 2 on. And it's not going by firing order here, it's just going numerically through. So as we look at number 3, we see a relatively equal drop. Number 4 drops, number 5 drops. Number 6, wow, we've got a significant less of a fuel drop than what we saw with the other cylinders. Same with cylinder 7 and also with cylinder number 8. So as we think back here, well, where was our misfire? That's right, it was cylinder number 6. And so we're definitely not flowing as much fuel through number 6 injector. We've got fuel trim codes, we've got misfires, we've got a lot of stuff pointing at number 6 injector. And so based on the mileage of the vehicle here and some of the other stuff, the fact that the rail was coming up, this particular customer said, you know what, I'm fine, we're gonna go on a trip with this one. Let's go ahead and replace all 8 fuel injectors at that point. This way we're ensuring that they've got a nice balanced system. How many times haven't you seen it where you replace one injector and 2 weeks later another one goes out? They've all opened and closed just as many times there. And so this is a great recommendation. I know sometimes it's hard to talk the customer into do that. And some states, some of those might be frowned upon unless the customer makes a request, as we've seen here. And so in this case, 4 injectors were replaced. The fuel system was actually flushed and the filter was replaced ahead of time also, which are great pieces to make sure that we're not contaminating the new injectors here. And that solved that particular customer's problem. So, as we wrap up the session here, let me review a couple things here. We've basically, in the short-term world, we've got our 2 different terms here. Short-term fuel trim is our immediate correction. Long-term is our longer, slower, more learned correction. We've got a lot of different terms here. Hopefully you've familiarized yourself with this, but don't be surprised if some of these additional terms show up on your scan tool at some point. And feel free to come back and refer to our presentation today to touch up on some of that. Remember, generically, we're adding our short-term and long-term to come up with our total term, and we want to actually look at the recorded or graphed data here. So much more important to observe the trends than we are just by looking at it, numbers changing in front of our face here. Lambda, if it's going to the right, if the number's getting bigger, it means you've got a lean condition and the vehicle's adding fuel. Conversely, if it's going to the left and the number is getting smaller, it means it's taking fuel away because you've got a rich condition. So it's trying to lean that mixture out there. So hopefully you've learned a little bit more about diagnosing vehicles using fuel trim strategies here today. The time's gone by pretty quick here, but if you want to learn more about this, always recommend that you go to our Standard Brand YouTube channel. You can find recordings of previous versions of these power hours, but you can also find a lot of our installation videos, and we've got some diagnostic tips there from many of our pro trainers throughout the years here. If you're looking for more information on our fuel injection program, you can see we've got a lot of different information here, as well as some helpful articles and more training aids. Go to standardbrand.com. All right, well, Corey, we've addressed a couple of those questions as we've gone through here, but do we have any other ones?
We actually do, Ryan. A couple of good ones, really. The first one caught my attention was, will ignition problems affect fuel trims differently than fuel injector problems?
That's a good question. So ignition problems will show up immediately, like if an ignition coil's shorting out or misfiring. We might see a little blip in the fuel trim, but it'll come back to the normal value. Now, a fuel-related issue or airflow-related issue is going to have a significant impact on the fuel trim reading. It's based on the amount of hydrocarbons going past the air fuel sensor or the O2 sensor there. And so, to summarize that answer, ignition problems are not going to have very much of an effect on fuel trims. Fuel injection problems or airflow problems will have a significant effect on fuel trims.
Very good. And then I have 2 questions here. I'm going to kind of put them together for you. The first is, do all air fuel sensors report in Lambda? And to go along with that, do all GDI vehicles use air fuel sensors?
Good questions. So one thing we've learned in the automotive world is you can't say always or never, right? And so GDI vehicles, a lot of them are newer vehicles, and a lot of newer vehicles will use air fuel sensors. Quite often the upstream application, but the downstream we're still going to see our traditional oxygen sensors in many cases. And then how do they report? Well, a lot of it depends on the manufacturer. If you're struggling with some of those and you're confused about them, again, I recommend you exit out of the OE side of the scan tool and go back to the generic side and look at generic OED information, which is standardized. Same information you've been looking at for years, and help you out with some of that type of information there.
And that looks like that is the bulk of the questions for now, Ryan.
Well, thank you very much for coming out. If you're looking for more information on some more training of this, reach out to your account representative. We've got full one evening classes related to some of this fuel stuff. I grabbed this case study out of one of those particular classes, and so we've got trainers around the country every night doing in-depth classes on this. I just gave you a small sampling here. But from all of us at Standard Pro Training, we look forward to seeing you at the next Power Hour.